Clogs are one of the most common issues you will run into when using your nano counter. In this video, we will go over what clogs are, how to identify them, and how to fix them. Nanopores are just nanoscale holes, and with molecules constantly translocating, things can get stuck in the hole and clog the pore. Clogs result in a sudden loss of baseline stability. Unstable baselines can have other causes, but clog is a catch-all term that we use to describe a sudden change in baseline stability. It is important to note that some reagents may cause severe clogging problems. If you notice that your pore consistently clogs with a certain reagent, it may be best to examine what in that sample could be contributing to clogging issues. Clogs can seriously impact the quality of your data. Clogs can halt translocation or make translocations indistinguishable from the noise. The noise from a clog may also be picked up by the software as translocations, making it hard to differentiate between a real event and a clog event. For these reasons, it is crucial to watch your baseline closely throughout data collection and address clogs immediately. Clogs come in many forms, so it is important to understand all of the signs of a clog. They include a baseline drop. A baseline drop is the most common symptom of a clog and can be very obvious or very subtle. Baseline waving, dipping, rapid rising, or falling. Jagged, fuzzy, choppy baseline, sudden thickening of the baseline, decreased pore size, or heightened IRMS. Most clogs will exhibit multiple symptoms, but occasionally a clog will manifest only as a slight baseline drop. The following are examples of various types of clogs. There are a number of steps to take to clear clogs. Each step is more aggressive than the previous, so it is important to follow these steps in order. Otherwise, you could cause unnecessary damage to your nanopore. Your first response to a clog should always be the zap function. Zap will apply pulses of high voltage to the pore, which is very effective at clearing debris. Zap will pause event detection, so you do not need to worry about zapping in the middle of a sample run. To zap, click the lightning bolt icon in the top right corner of the NanoCounter app. Alternatively, Option Z or Alt Z work as keyboard shortcuts. Many clogs require multiple zaps to be cleared, so be persistent with zapping. It is the safest and easiest way to clear clogs. If multiple zaps at the default 4 volts don't work, try increasing the zap voltage. Simply click the arrows to the side of the lightning bolt to change zap voltage. You may apply up to 8 volts when zapping. This is still a very safe technique to unclog your pore, so don't be shy with the number and intensity of zaps you use. If zapping is not sufficient, the next step is to stop recording data, remove the test strip, and flush both channels with buffer. You may use either your chosen running buffer or the provided nanopore startup buffer. Alternating between these two buffers may also be effective. Flush each channel 1 to 3 times with the buffer of your choice. Remember to switch back to the running buffer before continuing your experiment if you use the startup buffer to flush out a clog. When you're done flushing, dry and insert the strip back into the nano counter and turn on voltage to see if the clog is cleared. If flushing did not work, move on to a technique that we like to call aggressive flushing. With aggressive flushing, you will rapidly and forcefully push buffer and air through the test strip channels. To do so, take some buffer and some air up into your pipette tip. Insert the tip into either channel and rapidly move the pipette plunger up and down. Continue for 10 to 15 seconds in each channel. Flush fresh running buffer through each channel after you are done to push out any air bubbles that were introduced. Dry the strip and insert it back into the nano counter and turn on voltage to see if the clog is cleared. If all of the previous steps were not sufficient to clear the clog, as a last resort, conditioning may be used to regain baseline stability. Conditioning is a last resort because it is the technique most likely to change your pore and impact data quality. However, applying sustained high voltage pulses can be very effective at pushing a clog out of the pore. Before you get started, ensure that running buffer is flushed into both channels of the test strip. There are 2 options for conditioning for clearing clogs. The first is auto conditioning, which is the procedure used to start up a strip. This option is easier, but may be less effective for clearing clogs. Open the conditioning window. Set your stop size to 1 to 2 nanometers larger than the pore size pre-clog. For example, If your pore was originally 36 nanometers, set the desired size to 37 or 38 nanometers. Start conditioning. When conditioning stops, close the window and turn on voltage to see if the clog is cleared. The second option is manual conditioning. We will demonstrate using the same pore even though it is no longer clogged. With manual conditioning, you will direct the software what voltage to apply and for how long. Open the conditioning window and set your stop size as described previously. Uncheck the auto condition box. Boxes will appear which allow you to manually enter the voltage being applied to each side of the pore. It is most effective when the voltages are opposite in sign but equal in magnitude. To unclog pores, you will want to slowly step up voltage until you are confident that the pore is clear or the stop size is reached. It is important to pay attention to what the voltage pulses look like. An unstable pore will most often have pulses that are jagged and asymmetric. A stable pore will have flat, square pulses. If the conductance through the pore is increasing, indicating that the clogged molecule is exiting the pore, the peaks will have an upward slant. Start off at 2 volts on each side. 2 volts is not enough to unclog the pore. Observe the peaks. When you are ready, step up to 3 volts, then 4 volts on each side. 3 and 4 volts are also typically not strong enough to unclog the pore. Step up to 5 volts. Most clogs will not respond at 5 volts, but some might. Look for an upward slanted peak to see if the conductance is increasing. If so, stop increasing voltage and let it reach the stop size. If it is still not gaining conductance, increase to 6 volts on each side. If necessary, go up to 7 volts on each side. By now, most pores will have responded with 6 or 7 volts. Occasionally, a pore may need 8 volts, but be cautious. At these higher voltages, rapid pore degradation is more likely, so give the pore just a few pulses of voltage and then stop conditioning quickly. This method is effective, but tricky, so be diligent and use caution. Close the conditioning window and turn on voltage to observe the baseline. If the baseline is still unstable, your pore may not be salvageable. You can try to continue conditioning, increasing the stop size, but even if the pore regains stability, your data quality may change. Most clogs will clear using the above steps, but some are very persistent and can destroy the pore. If you are unable to unclog the pore, finish your experiment, note what happened for future reference, and take a final pore evaluation. We hope this video has been helpful for you to understand clogs and how to deal with them. If you have any questions related to clogging, please contact support@ontera.bio.